Shuheng. So since I'm going back to Stanford on Sunday, Shuheng asked me to report on what I was doing at the institute. So I'm well, that's what the talk is about, to some extent. So I'm going to talk about quantum field theory in de Sitter space. I will start with a short introduction and motivation. Then I will review on sort of what the focus of this talk is that this problem of infrared divergences that are sort of generically present in perturbation theory. And then I will explain the formalism that resolves, in particular resolves these infrared divergences, but in general it's something, sort of a new way of treating quantum field theories in de Sitter space. And then if there is some time, I will talk about some generalizations of the formalism and maybe some applications. Okay, so let me start with the motivation. I guess the first question is why can we be interested in studying quantum field theories in de Sitter space? Okay, so I guess our sort of, I don't need to explain why we're interested in studying gravitational theories in de Sitter and in general in cosmology. We live in a cosmological expanding space-time. Eventually, we want to understand what it is. Maybe eventually, what is the origin of initial conditions. Some sort of, I don't know, holographic or non-perturbative definition of de Sitter space or quasi-de Sitter space. But these are sort of very complicated questions. Unlike in ADS, where we're lucky and we right away got some non-perturbative definition, including gravity. In de Sitter space, we don't have a very good candidate. So the idea here is to first understand quantum field theories really well, so that maybe it will give us some hints for how to proceed with these bigger questions. Okay, QFT. And then sort of a second motivation is that there are some subset of problems they are already present in quantum field theory. In particular, as I will argue, this core of this problem of infrared divergences, it can be formulated just within quantum field theory. It's not so much related to gravitational perturbations. So there are some problems that we can address directly in the framework of quantum field theories, and then gravity will just give some sort of small perturbative corrections that we can include later. Okay, so that was the introduction. Let me go now to this actual problem that I'm going to consider. Before getting there, let me just review some very basic properties of de Sitter space for you, because maybe not everybody is thinking about it all the time. So there are different ways of drawing de Sitter space. One is by having a Penrose diagram like this. Okay, so Penrose diagram of de Sitter space is basically a square. We can consider some observer that lives along that line. And then this observer has something like something called static patch. Okay, so this observer sees a cosmological horizon. Okay, and this triangle part is something accessible to a single observer. And this is also the region which we can cover with a time-independent metric. Okay, so the for me, in this talk, the theta space will be basically identified with what's called expanding Poincare patch. It is this region, okay? Well, of course, if we can serve the entire expanding Poincare patch, we can subset of this manifold is a static patch, so that's included. But this is the main focus, is to consider this expanding patch. Well, we can discuss the contracting region later on, but for some cosmological purposes, it doesn't appear very interesting. Okay, so I will mostly be using for this Poincare patch, I will be using sort of FRW coordinates. That's when we write the metric in the following form. And this scale factor goes like e to the ht, where h is the Hubble constant. That's the parameter of the expansion of the zeta space. So you see, when time goes on, sort of the physical size of our coordinate patch grows, and on this picture, this FRW coordinate, the constant time slices, they look something like this. Okay. So there is another way of drawing the zeta space rather than the Penrose diagram is just sort of drawing the global de Sitter space as a hyperboloid. So then it looks like something like this. Well, it's a poor drawing of a hyperboloid, but anyway. So this is the global de Sitter space. And then Poincare patch is it's some upper triangle part like this. And just one point, just to make it, that at late times, when this hyperboloid is large, it's not very important whether we consider this global slicing, which is something like this. Maybe let me do it with a different color. If we do global slicing, which is just has a topology of a sphere, it looks like something like this on this picture. And unless we are really interested in correlation functions that are of a sort of overall size of our universe, there isn't much difference between this Poincare slicing and the global slicing. So physics is the same. Okay, so it sort of suffices to consider this Poincare slice to get a general picture of what's going on in the Sitter space. Very good. So now let me go to this problem of the actual problem of infrared divergences. So let me first define. So the strategy here is the following. So I'm going to formulate the simplest non-trivial case where this problem arises, and then I'm going to solve it in this case, and then we can sort of discuss, okay, how general a solution is. The idea is the solution is general. So let's not try to solve, this problem in some most general case possible immediately. So in particular, I will consider. So as I sort of anticipated from the title, there is no fluctuating metric. It's just fixed background of this form, on which I put quantum field theory, the simplest quantum field theory, interacting quantum field theory I can put here. Is just going to be lambda phi to the 4th theory. And the equations that I will write, they're going to be in 3+1 dimensions. So I just want to make this point that the physics is in the Sitter at long distances is very much independent of the number of dimensions that we consider. Okay, so it's pretty much the same in any number of dimensions. And also the actual shape of the potential is not very important, okay? But because I'm interested in infrared cases, I will always think that mass is much smaller than Hubble, okay? Doesn't mean that what I'm doing does not apply when mass is bigger or comparable to Hubble, but that's just the regime of interest. Okay, and the rules of the game is that I want to calculate correlation functions in this theory, say at equal times, but at large coordinate separations. Okay, something like this. So the measure of success is, are we able to compute this sort of correlation functions? So because we talk about correlation functions, we sort of need to specify the state in which we're computing. So again, I'm going to choose some state that is sort of preferred state in the ether space. We're going to compute correlation functions in that state, and then we can discuss whether, well, we can argue that the answer is in some sense state independent, okay? And there are many names for this preferred space in the ether space. There is it's sometimes called Hartle-Hawking state, sometimes called Bunch-Davis state. It's sort of all the same things. And just in a way, because part of the things that I will be doing perturbation theory. And perturbation theory is just given by I epsilon prescription. Okay, that's just sort of, I will explain it in a bit more details how this I epsilon prescription is implemented. But sort of the most naive thing you do in perturbation theory lands you on this state. And then the physical meaning of all those states is that when we go to very short distances, okay, then the space-time should look like it is a Minkowski space. So this is just from some general intuition. If we go to distances that are very, very small compared to the curvature scale, it should look like flat space. And either of these four definitions gives us the same state. Okay? Good. So now you may say, well, that looks like a simple theory. And well, of course, just to be able to compute something, I will always take lambda being much smaller than 1. And you say, well, okay, this is just some perturbative quantum field theory. Let's just set up a bunch of Feynman diagrams and just compute this correlation function. Sort of what is the problem? So let me review for you what happens when you actually try to do this. So usually, again, it doesn't matter so much, but just historically, these calculations are done in sort of mixed representation in a sense that time is kept real, and it will be going up on all my diagrams, and then this coordinate x, it gets transformed to in momentum space. This is just k is just 3 momenta in my case, okay? And then we just draw a bunch of Feynman diagrams. So it's in correlation functions. There is a slightly more complicated set of Feynman rules than it is in flat space, but you can work it out and start computing. Okay, so first, say we compute a 2-point function. Okay, so then we have some diagram like this. Then, so that's always time. Then there is a slightly more complicated diagram like this. So this line is the time at which I'm evaluating my correlation functions, right? And this transverse is a coordinate or momentum direction. And then there are sort of even more slightly complicated diagrams like this. So when you actually go and evaluate them, what happens is that if this thing of order 1, because it's a free theory, then this thing ends up being something like lambda over m to the 4. And this thing goes like lambda squared over m to the 8. Okay? And every time there is some units issue, it means that there's a Hubble. Okay? So technically, this comes from the fact that this the propagator, the line that I'm drawing with the propagator, I mean, there are several propagators, but doesn't matter. All of them have sort of, there's at least one of them that, depending on the basis that one is using, there's always a propagator that at low momenta behaves in the following way. it goes like 1 over k to the 3 minus m square, and then there is also a to the minus m square. So, and then if we look just at momenta integrals, okay, that we need to take in these loops, they're always integrated d3k, so they spit out this inverse powers of the mass. And then if we try to set the mass to 0, then this becomes some logarithm divergences. Okay, so that's how they're usually presented. But I like to keep a small non-zero masses, sort of never late to take it to 0. And actually, m equals 0, there's nothing special that goes on when m is 0 and m is slightly negative in this theory. So, and also mass gets renormalized in the UV. So it's good to keep some small mass. So we see that there is a problem if lambda is bigger than m to the 4 over h to the 4, then this series, they badly diverge. Okay? So now you may say, well, okay, we've sort of seen divergent series in other situations. Maybe we can just go and like resum them in some way. So people tried. I think the most sort of the state of the art of this is a paper by Raman Sandram and Matthew Baumgart that appeared like less than 2 months ago. So, well, they resum something, they get somewhere, they get the leading answer for one-point functions. Okay, so this is sort of how far you can get. And okay, I mean, I don't think they say that they cannot even prove that the subleading correction will actually, I mean, what sort of naively is subleading, that it will actually be subleading at long distances. So it's not even sort of a systematic, completely systematic resummation. But maybe it can be done. I mean, I'm not saying that it's impossible, but at the moment, nobody managed to resum this sort of diagrams. Good. So this is the problem. So the idea is that we're going to have a formalism that does something completely different and addresses this problem. Mm-hmm.
Would you see this problem if you remain just in the static patch of the system?
Yes, yes. You would see okay, so I just for simplicity, as I said, like to do something, I start with equal time correlation functions. The formalism that I will present, it will also apply, I mean, the slight modification, but we can also compute non-equal time correlation functions, and the same issues arise. So there is no known like simple perturbative way to compute even within one static patch. Which, I mean, I think there should be a formalism which, if you are interested in the physics of static patch, you can compute it being uniquely within static patch, but that wasn't done. Mirbabait, I think, tried to do something like this, and he also roughly computed like the leading answer to one, maybe leading answer to 2-point function, leading answer to 1-point function, something like this. But
can you just say the usual, like the standard, at least intuition about this is that you have your lambda phi to the 4. You're at sort of finite temperature of order Hubble, so phi is just going up the potential. You have to see that phi is an expectation value roughly so that lambda phi to the 4 is comparable to Hubble to the 4th, but then the size of phi is a 1 over lambda, and that's
yes.
Why there's something.
Exactly, yeah. This is one of the ways to see that something like this is going on, and indeed, this is the right intuition. It's just, okay, the question, how do we organize it into some systematic way? Yeah, and one thing, yeah, I should say that
that is the answer for the 1-point function. It's roughly 1 over 4th root of lambda.
good, yes. The answer for the 1-point function sort of was known since long time. Just the answer for all 1-point functions is given by the single point distribution, which is e to the minus v of phi divided by h to the 4. And, so from this object, you can compute all the 1-point functions, and that's that's something that was known since whatever Stravinsky's early work on inflation. I should say that I decided I'll try to sort of go in the order which is opposite to usual. I will first do like the calculation, okay, And then I will try to explain some intuition that's behind this calculation. So the reason for this unusual choice is that somehow historically, different people had different intuitions about this problem. And okay, I mean, it's sometimes good when we can, I mean, intuition is great, but if we can just do calculation and not argue whose intuition is better, that somehow gives shorter way to the to the final answer in some cases. But sure, yeah, what Nima said is correct. Like this can be guessed.
That's the nicest way anyone has ever told me to shut up and calculate.
Okay. Okay. Any other questions? Okay, and as I already said, this formalism that I'm going to show is to a large extent inspired, let's put it this way, by work of Stravinsky back in the 80s. So as I said, it's a little bit complicated, the construction, but I'll try to show you at least some technical pieces of the calculation, so at least you get sort of a spirit of what's going on. Yeah, I won't be able to like derive everything from scratch in 1 hour, but roughly the procedure consists of 4 steps. Okay, first is going to be the calculation of the wave function. Well, as I said, in this Bunch-Davis state. Then I will perform some split into long and short modes, okay, and define some probability distributions for long modes, okay. Then the next step is we're going to derive some partial differential equations for these probabilities. They will be called PNs, okay, these probability distributions. And then after we solve these partial differential equations, this will give correlation functions. Correlators. Okay? So these are sort of the four steps through which I'm going to take you. Okay, let me keep the metric for now and the Lagrangian. So, okay, let us start. Let's start with the wave function. The first observation that is crucial to make here is that the wave function is IR finite. Okay? So the shortest way to guess that this IR finite is if we remember the relation between the wave function in the theta space and partition function on Euclidean ADS. Namely, at least if there is no gravity, which is the case in question, and in perturbation theory, that is also what we're dealing with, we can put the same theory with the same Lagrangian into Euclidean anti-de Sitter space, okay, and then which will be function of some sources, okay, and formally it is a function of the cutoff on which we are putting our boundary, okay. So we sort of need to think not about the renormalized ADS partition function, but the one with the finite cutoff that is put at some value z, and then if you change z to I eta, where eta is a conformal time, I'll define it in a moment, and L into LADS into I Hubble inverse, okay, then what we're going to get the wave function in this favorite state of mine. This is again a function of fields and the conformal time eta. And the conformal time for the Sitter is when the metric is written in this form. Okay, so this is now very, I mean, there is some Hubble squared here. This is something very similar to, of course, Poincare slicing of Euclidean ADS. Okay. Good. So I will be sort of oscillating between using these coordinates and using these coordinates. The slightly counterintuitive thing is that when time goes upwards, eta goes to 0, because eta is always negative. So this eta goes from minus infinity to 0, and 0 is the asymptotic future. Okay, as it is, z is asymptotic boundary in ADS. Very good. So this is something that I guess Juan was the first to point out, and well, this also explains the conceptual difference between calculations that we want to do, or at least we want to do if our goal is to compute this correlation functions between what we do in ADS and what we do in DS, right? So what is sort of the final answer usually of interest in that de Sitter space, in de Sitter is just the wave function, okay, which is still related to correlation functions by some additional path integral, okay? Good. So just to make an immediate comment, of course, step 1, I have 3 more steps. You could say, okay, we have the wave function. Why don't we just compute correlation functions by taking something like psi star, inserting a bunch of these phis, and integrating d phi, right? In principle, this gives correlation functions, but it is this path integral that is still infrared divergent exactly in the same way. Okay, so this doesn't solve the whole issue. It's just a step 1. And yeah, I think it's just an interesting question. What's the relation between the wave function and the correlation function in some general case? But I'm not going to discuss it much. Good. So I want to say that it's not necessary, of course, to think about ADS to see this IR finiteness. Okay, we can instead just use perturbation theory and solve the Schrödinger equation, functional Schrödinger equation for this object perturbatively, and of course we will arrive at the same answer. And there, just the technical piece of the calculation is that when we compute the wave function, again, I will have some set of Feynman diagrams. Okay, that's just very similar to Feynman diagrams for Witten diagrams, if you like, that we use in ADS. But then this propagator for the wave function, it's a different propagator. Maybe I can do it sort of wiggly like this. And this guy goes to a constant when k goes to 0. Okay, good. So once we do this calculation for the wave function, let me roughly sketch for you how the answer looks like.
Isn't this more, I mean, I thought you wanted to say that it actually goes to 0 as eta goes to 0.
Well, okay, so we need to, when I take k to, of course, everything that matters is always k a minus 1, right? The physical momentum. So I'm being a little bit sloppy. When I take k to 0, I really mean either time fixed and k to 0, or really I mean this thing to 0.
No, but what I'm confused about is that the propagator goes to, you said the propagator goes to
some number. There's a
constant. It doesn't vanish as eta goes to 0?
No, it doesn't vanish. It goes some constant, I think. I mean, if it vanished, it would be even better. I mean, but I don't think that I think just it goes some number. For massless field, I think it just goes some number. All what matters, of course, if this integral.
That there's an extra 1 over eta. Never mind. No, yeah. Okay.
Yeah.
Yeah, it goes to a constant.
I think in k, yeah.
Sorry, Victor,
Uh-huh.
so what's the difference between those two diagrams? What's the difference between the solid line and the
Yeah, so the solid line is sort of perturbation theory directly for correlation functions. The wiggly line is a perturbation theory for the wave function.
The difference is that when you're computing the wave function, you have to have vanishing boundary conditions.
Yes, it's
you want the fluctuations to vanish at eta equals 0. So so instead of Feynman propagators, you have a Feynman propagator plus a correction, which is just a solution of homogeneous wave equation, but such that it vanishes on the boundary. In flat space, it vanishes. In de Sitter, just because it's a little bit definitional, but because of the mapping to eta variables, there's an extra 1 over eta, so it goes to a constant.
This is because we're computing the correlation function and not trivial wave
No, no, no.
Just for computing the wave function.
Yeah, so when you compute, I mean, think of it as a path integral, right? When you compute the wave function with the path integral, sort of fix future boundary conditions, right? Because you say path, you freeze value of the field at the future infinity. And
For the wave function, what are those 2 points?
oh, yeah, these are okay. Let me write one more equation, and then it will be clear. So when I compute this log of the wave function, right, I expand it in the powers of fields. So there is there will be something which is quadratic in field plus something that is quartic in field, and then so then these are usually what coefficients here are like correlation functions in ADS. Okay, and here just some coefficient functions that I can compute by this sort of diagrams. Okay, any other questions? Okay, let me actually tell you what the answer is. I'm not going to derive it. It's just a bunch of calculation of Feynman diagrams to some order that we need. The first piece here is actually divergent when eta goes to 0, and it starts with the potential term, then there is something like v prime squared and plus dots. Then there is another piece which is still imaginary. It is still divergent, just by weaker power, and it looks like it's a gradient term. Okay, it's phi Laplacian phi. This is a 3-dimensional Laplacian. And then there are again dots, and then finally there are terms that are real and finite. And they look like expectation values of some operators in some sort of CFT. Plus dots, and then there are some terms that are subleading when eta goes to 0. Okay, so these are the pieces that in ADS are usually counter terms that you sort of throw this away, but in this approach of mine, they will actually be very important because they're actually the largest. And this is the part which is the log of the partition function of some CFT. At least it has the symmetry properties like this. So now I need to say, when I say that it's IR finite, it means that I can make sense of this perturbative expansion. So when is it true? Because in principle, wave function is defined for all values of phi. So how do I compare terms that have different powers of phi? And the rules of the game, the claim is that this expansion is actually perturbative if phi is smaller than lambda to the -1/2 Hubble. As Nima already anticipated, in fact, we will get that phi is of order lambda to the -1/4 Hubble. Okay, and so this will be satisfied. But what we're going to do, we sort of assume that it's true and then check it a posteriori. Good. Okay, so we're done with part 1. Let's go to part 2.
Sorry, it's important to you that you're in 3 Poisson dimensions, right? Like in 2 Poisson dimensions, for example, we would have had a log.
Yeah. There are. Yes. So okay.
It's just from the
It's
the boundary propagator part. Not even
yeah. There are some logs here that I sort of ignored. I mean, I'm sort of trying to stress technical issues that are important. Those that are not important, I drop. But you are right. In any number of dimensions, there are some logs present in that expressions. These logs are always subdominant, for example, to this term. Okay. And again, well, I should. In the next step, you will see that I split between long and short modes, and actually what we care about is going to be sort of there will be logs of this cutoff, and again, those logs will be small. So those logs are not important to leading order, that's why I dropped them, but we can show that they're not important. But they're there in any number of dimensions.
This singular structure remains the same in whatever number of dimensions? It's always 1 over 8?
It's 1 over eta to the d, where d is the number of spatial dimensions. Yes. Other questions?
It's just like the counter terms that you implement to get the action finite.
Exactly. They're always local in particular, but it's not super important for me. Well, it's important that the leading term is local, if you like. That's what's really important. Even subleading terms are sort of not super, I mean, they're not ultra local anymore. But other questions? Good, okay. Let me go to the next step. It's a split between long and short. Okay, maybe I'll use this part of the blackboard. Good, so I'm gonna divide my field into short and long, where the long part is defined as fields with momenta that are with absolute value bounded by lambda of t, where lambda of t is given by epsilon a h. Okay? So what is this? So a times h, it is the inverse physical size of the horizon at any times t. Okay? While epsilon is going to be some small number. In fact, it's convenient to pick it as smaller than, much smaller than any power of the coupling constant. But we're going to make it larger than something exponentially small in the coupling constant. Okay? So this choice, I don't know, it may appear a little bit arbitrary to you at the moment, but you should think of this epsilon as some sort of RG scale. So it appears in some intermediate calculations by cancel out of all physical answers. So we're free to choose it whatever we want to make the calculation efficient. And you will see in a minute that this is the choice that makes the calculation efficient. Good. So now after this split, note that this, unlike unusual effective field theories, here the split between long and short modes is done in a time-dependent fashion. And that, of course, forced upon us by structure of the Sitter space, where metric is time-dependent. So we also need to choose our cutoff in a time-dependent way.
But you choose the time dependence in a very specific manner.
Yes, yes. I choose it in a way sort of consistent with the Sitter invariance, that my cutoff is at the fixed number of physical horizon scales. Okay? And okay, it sounds natural, and you will see that this is.
Why not that to some power? A to the n, h to the n. Why
No, but it's just this is just in by dimensional analysis, right? This is cutoff on momentum, so it's a scale. I mean, it's a scale in the units of momentum. I mean, horizon. So I think I erased my Penrose diagram, right? But so sorry. So when I had the horizon, right, this size of this Hubble patch is in coordinate space is ah to the -1, right? Which in momentum space it's a times h, and I make my split very far outside of the horizon, but not arbitrarily far. Good. Yeah, let me proceed with this, and then we'll see why it works, and then maybe we can discuss if there are alternatives. Good. So now let me define this probability distributions, as I promised. So probability distribution is going to be a function of n variables, coordinate distances between the point, and an explicit function of time. And it's just defined in the following way. It is integral d phi psi star with a bunch of delta functions of long modes. Okay? So you see, I almost just, if there were no these delta functions, I would just be computing 1. Okay, which also gives the correct normalization for these objects. They're just normalized to 1. But instead, I fixed a finite number of long fields. It's a priori chosen spatial locations. Good. So this is the end of this part 2. Now let's move to part 3, which is the derivation of evolution equations for this objects Pn. Is something unclear?
Where did the short? You haven't done the short long split. You've just defined this.
I just defined this for long modes, okay? And so physically what's going on is the following. So when we write this formula, it's physically clear that it's actually the long modes that's going to be large. And instead, short modes will be of order Hubble. So if we're interested in leading answers to correlation functions, it will be enough to just compute correlation functions of long modes. It will be leading answers to everything, especially at long distances. Of course, at subleading orders, we will be using phi short as well. So what I'm doing is some sort of like exact RG a la Polchinski. I'm not integrating out short modes. I keep both modes. I just treat them differently. Okay? And now I'm describing the procedure how to treat long modes on their own. And that's going to give the leading answers already. But we can systematically compute interactions between long and short, as I'll show you in a moment. If I have time. Yeah, I think I'll have time. Good. Okay. So now let me. So there is some sort of index long that should be for this piece, but there's just too many indices, so I don't write it. Okay.
I have a very stupid question. Why isn't this formula just psi mod squared evaluated at phi equals? Sorry.
Yeah.
Just say this again.
Yes. Yes.
Why aren't the integrals eaten up by the?
No. Well, because I'm tracing over. I'm taking this trace over all points, positions of long modes, but finitely many. And this is a very complicated integral. So you can think of this as an expectation value of this delta function integral. So if we were to compute it directly, we would run into all the infrared problems immediately. But we will not. We will pretend that we don't know what this sub psi star is. Okay? Instead, we will resort to Schrödinger equation and derive time evolution for these objects. And that's something we will be able to solve. Okay, let me make a few more steps, and I think it will become clear why I did it.
You're only fixing phi on a finite.
You're only fixing phi at a finite number of points.
Finite number of points.
Phi I, you meant phi, in the path equals phi at xi, which is nailed to phi L of xi. That's all I know.
Yes, yes. Phi long, and long is defined in this way. Yeah, and n is just 1, 2, blah, blah, blah. Okay? Good. So let's see how these guys evolve in time. So we take dt of Pn. There are two pieces that historically they were called drift and diffusion. Okay. So drift piece is when the time derivative acts on the wave function. Wave function depends on time, right? And diffusion piece is when time derivative acts on phi long, because definition of phi long explicitly depends on time. These are the only two things that depend on time in this equation. Okay, so I think I can show you some derivation of the drift term for P1. Okay, that's probably as much I can do. So let's do this. Let's divide the drift term for P1. Okay, so to do this, we first remember how the time derivative of psi star looks like. Okay, well, this is just something called continuity equation. Okay, it is d by d phi of psi d by d phi psi star plus complex conjugate. Okay, everybody is familiar, I hope. This is of x, and they integrated over x. Good. So now this is sort of an important point. To evaluate this d by d phi acting on psi or on psi star, I'm going to use my knowledge of the wave function. Okay. Let me go here. Yeah, maybe I'll use this part of the blackboard for a moment. So when I evaluate this d by d phi acting on psi, I get something that I'm going to call p. Actually, okay, there is a to minus 3 in this expression, whatever. That's how properly Hamiltonian defined. But never mind, a to minus 3 d by d phi acting on psi. I will call this sort of momentum operator, roughly speaking. Maybe we can put an I here, acting on psi. And because we know what psi is, we can evaluate this object. Okay? Note that because there is a variational derivative and we're going to integrate it, it's only variation derivative with respect to the long part that's going to survive in the equation. Okay? And this is important. Now let's evaluate what this pi long is. Well, let's just look at our expression for the wave function. The leading piece is just v prime of phi. Okay. Then there's a subleading piece, which is v prime squared prime. Okay. Then there is the piece, the next one that comes as a gradient term, but the gradient term is suppressed at least by something of order epsilon squared, right? You see why? Because I'm interested in the long part of this object, and when I take the long field, its gradient is by definition smaller than epsilon squared. Okay, so what I get here is something very, very small. It's exponentially small decoupling constant, so I can drop it. Okay, good. So we take this thing, we substitute it here, we substitute it here, we substitute it here. Then we take this derivative, integrate it by parts. It hits a delta function, okay? Then it becomes a derivative with respect to phi I, and then we pull it out, okay? So what we get that dt of p1 is d by d phi 1. Okay, it's now a regular derivative. That's now with respect to this thing. Times an expectation value of this operator pi long times, again, p1, given that I'm keeping fixed value of the long field at position x1. Okay, this is just this notation. So it's bracket phi 1. That's what it means. Is that clear? I mean, this are really elementary steps, like substitution, integration by parts. Good. So now let's see what this is, because this is sort of the crucial part of the derivation. So to leading order is just this object. Okay. So let me write what this is. Okay. So to leading order, this is just expectation value of lambda phi cube of x1. Okay. Given that phi 1 is fixed. Okay. Phi splits in long and short modes. The leading piece is when I just keep the long ones, but the long ones I fixed. So this is just lambda phi 1 cube. Okay. Then there is the next piece that comes from the fact that in these three modes I can take two short modes and one long. Okay. So that gives me lambda phi 1 times the expectation value of phi short squared of x1. Okay. Then there are other pieces. There's a piece that say comes from here, which is lambda squared phi 1 to the fifth. Well, with some order, I mean, I'm dropping, of course, order 1 coefficients. Okay. Then there are the more subtle pieces, because look, I'm interested in the long part of my momenta. But three long modes, they can make one short, right? So I need to project back. So there will be a piece which is, roughly speaking, something like this, which is a projection onto, say this is a projector on long modes of this object. Okay. Let me sort of explain you what these terms are and why they're important. Well, that's sort of the leading term. And it is pretty self-explanatory. I mean, this term is also, it's subleading given that counting, and it's also very simple. Now, this term has an expectation value of short modes given phi 1 fixed. This is, roughly speaking, this diagram that was over there, and that was divergent. Okay? This diagram will behave like logarithm of epsilon, because now it's only short modes, so I cut off at epsilon. This is where this requirement is coming from. I want log epsilon times square root of lambda to be much smaller than 1, so that this term is much smaller than this term. Okay, you see where square root of lambda came from? It's from 2 powers of the long field. Okay, good. So now let me briefly discuss with you this term, because this was sort of the technically probably the hardest part. How to deal with these terms? We want to Fourier transform. To Fourier transform, we need to know the long field at least. So it's this projector that depends on x2 and x1 Okay, because I want to project back my object on something that only has support with Fourier modes that are smaller than lambda. So I need to know the field at least at one more point, okay, to do this Fourier transform. And this is where I write this as the following. I write it as an integral over the second point, then it's an integral over the field at the second point, then there is this projection, then there's lambda phi cube, and then there is a 2-point distribution. Okay, so these terms, they couple distribution with with different number of legs, and this is where the miracle happens. Okay, this is how we avoid actual problem of infrared divergences. Every time I have an insertion of a long field at some other special point, instead of doing a path integral over it, I will just insert another delta function. Okay, and I will push the problem to later. I will express it through the higher point distribution, in this case through P2. And then again, a posteriori, we can justify, once we compute this P1s and P2s, we will show that this term is smaller by actually full power of lambda than the leading term, okay, and so on. Good. So this is more or less the definition. Okay, I mean, we need to plug this one here, and that gives us the derivation of the first few terms in the drift for P1. So there is an analogous machinery for the diffusion term. It's slightly more complicated, but you basically repeatedly run into expressions like this. But the thing is that, okay, there is no magic. We can just estimate them, compute, or at least estimate them easily from our path integral representation. Okay, instead of, yeah, is it sort of that was sort of the most technical part that I wanted to show. So if there are any questions, I can go in more details. If somebody is curious, I'm happy to explain, like in billion details, how we deal with this time derivative, with these delta functions. But it's basically the same sort of procedure. Let me show you instead how the answer looks like.
This term is the analog in sort of Wilson-Polchinski of the tree exchange, of the ds d phi squared. It's like all the long modes can produce a short mode.
Yes,
So
yes.
There's also the like loop analog of that. Is there an analog of the?
I guess I don't remember well enough Wilson Polchinski, but
I mean, that equation just has two pieces. One is the derivative of the effective action squared, and then the other is the double derivative of the effective action on the right-hand side. Both are just taking into account that the long things can produce a short.
yes. So there is a more analogous piece. Yes, there is a piece over here in this diffusion term. Yeah, there is a piece where basically you say that like a bunch of long modes can source a short modes. So basically, when we take this path integral over short modes, so this sort of path integral, compute this expectation value, we treat long modes as like a background field, right? And because my background field has non-zero momentum, it can produce a long mode. Again, this contribution will be proportional to like P2 or P3, and I can estimate them, and they're small. And it's exactly sort of how calculation of this term goes about.
So I think that second term is like is coming from the derivative.
Yeah. Yes, yes, and of course that's why epsilon drops out, because there are terms which are here and here that have very different nature, but sort of opposite in a sense. It's short mode sourcing long and long mode sourcing source, and one is here, one is here. When you add them up, of course, epsilon dependence cancels, but individually each term depends on epsilon. In particular, this term you see explicitly depends on epsilon. This term, when evaluated, also explicitly depends on epsilon, of course. Other questions? Okay. I have about 6 minutes left, I guess. So let me show you what the answer is after all these procedures carried through. So to understand the answer, we need to define two partial differential operators. The one particle differential operator, one field differential operator gamma I, and an operator gamma ij. So here it's just gamma I written out to leading order. You see it's a second order differential operator with respect to field at a single location. This piece is just the leading part of the drift term that I derived for you. This is the leading piece of the diffusion term that I didn't derive for you, but that we briefly discussed with Nima. Operator, the two-particle operator, it just consists of the diffusion term to leading order. Good. So once these operators are understood, there's the following hierarchical system of equation. So you see I have like dtp1 acting with the some operator acting on p1 plus some operator acting on p2. But this operator is always subleading to this operator. The same happens for p2. To leading order is just some differential operator acting on p2. And etc., etc., etc. for any pn. And then there are initial conditions for these equations that when time goes to minus infinity, pn just becomes a bunch of delta functions times p1. Okay, and this again you can derive, but intuitively it's clear because when importantly, I keep coordinate positions here fixed, which means that physical distances between those points, they all go to 0 when time goes to minus infinity. That's the origin for all of these delta functions. Good. Now, okay, so this is basically the answer. Let me show you a little bit how the solution of this differential equation comes about, how it looks like. So in principle, at this point, the problem is solved. Okay, it's just a bunch of partial differential equations to any finite order in lambda. You only need and if you want finite leg correlation functions, you only need finitely many equations. Roughly speaking, if you want to compute k-point function with the precision lambda to the m, you need to go up to pk plus m. Okay, so this is number of points, this is number of precision, and this is how far we need to go into this chain of equations to find the solution with that order. So we can in principle just put it on the computer and it sort of does it, but we can do some things here analytically. Okay. So not surprisingly, because it's basically like Schrödinger equation, right, in Euclidean time. There is dt of something is equal to second order differential operator on the right. So not so surprisingly, everything's properties of solution are determined by eigenvalues and eigenfunctions of these differential operators, okay? In particular, for P1, let me just rewrite here. So for P1, I just have this gamma phi acting on P1. So once I find eigenvalues and eigenfunction of gamma, I find everything. So now the zeros eigenvalues. So now let me define eigenvalues and eigenfunctions of gamma. So this phi n of phi is an eigenfunction with an index n. Okay. So the zeros eigenvalue is always equal to 0. Okay, and the zeros eigenfunction corresponds to the 1-point equilibrium distribution that already Nima guessed. It's e to the minus v of I h to the 4. So you can check that it's always a eigenfunction of this differential operator. Now, important point. So this sort of solves problem of 1-point functions. So now to find 2-point functions, we need to solve this slightly more complicated equation. Here it's important. So there is this little plot of how this operator gamma ij that explicitly depends on distance and on time, how it changes with distance and time. Namely, it starts as 1 at early times, and it goes to 0 once separation between points becomes comparable to lambda minus 1. Okay, not so surprisingly, that's when my points start being causally connected. So that means we can use sort of sudden approximation in quantum mechanics to solve this differential equation for second one. After you think about it for a little bit of time, it becomes apparent that at long distances, 2-point functions, as well as all other correlation functions, they decay at large distances is given by non-trivial eigenvalues of this differential operator. Okay, this is sort of the exponents with which everything decays in space, but actually the same is decay in time. In particular, to leading one, it will be the first eigenvalue of this differential operator. That's something we can only find numerically. It's some Schrödinger equation with some random potential. free log.
Just the 2-point function for massless scalar.
It does not exist. It got, you see, if we go to short enough distances, we can expand it and there will be a log. But all those logs got resummed and produced something very non-trivial. Produced this power law decay. So it's as if there was a mass of order of this eigenvalue, and this eigenvalue, lambda 1, is just some number, like you can do it on mathematical, like there is no analytic expression for it, but it is of order square root of lambda. Like I should say that this problem is sort of strongly coupled. Coupling constant just factors out. I mean, we can do a change of variables here, and coupling constant just sits in front of it. Okay, so it's a Schrodinger differential operator, which is like after change of variables, it's not lambda phi to the first, like lambda phi, it's like phi to the 6 plus phi squared without any lambda. That's sort of the problem. That's the problem that we're solving. Okay, so I mean, I'm solving this equation. I can define phi tilde, which is lambda to the minus 1/4 phi, and I can define capital phi tilde, which is e to the minus something like v over 2 phi. And in these variables, I'm just solving d by d phi tilde squared minus phi to the 6 plus phi squared, something like this. So it's, and then there is a square root of lambda in front of it. Okay, so this is the problem, that the technical problem that we are solving. Okay, and that governs the decay of correlation functions at large distances.
Sorry, I'm a little confused. So are we matching to like usual? Let's see. Does it? It bugs me because the usual log we see in inflation. Where is the usual log we see in inflation?
Well, okay, so this is, yeah.
Inflated so long that
yes.
That it's crawled up the potential enough so that it's
yes.
active, and that's where this is coming
Yes.
So is this applicable for what we care about with actual inflation?
Well, no, it depends what we care about. So for the inflaton, for single field inflation, for the inflaton, no, but this problem just this IR divergences do not arise if you have enough shift symmetry. For the single field inflation, for the inflaton, this problem is not there. This problem is there if you have like a second field. Yeah, maybe it also came a little bit late, but I was explaining that, yeah.
So that's the point. Here we're imagining we're inflating so long that this the dynamics the rough dynamics we're talking about that lets the scalar random walk up to the
yes.
the height of
The scale is not the clock field. It could be like in this regime of eternal slower inflation. Either or this is just an auxiliary field that we care about.
This really is solving the problem of officially. I mean, for a massless field, there's no propagator.
Yeah. For field with exact translation invariance, like massless has no potential, there is no problem, and then we need to twig a little bit the formalism. Yes. So I was somewhere probably said that if I'm in this regime. Okay, then mass only gives some subleading correction here. Roughly, this, if you like, there is a term over here which is m to the 4 over lambda phi squared. Okay, so if mass is large enough, then this becomes a harmonic oscillator plus small corrections. So we can do it analytically and perturbatively. And if mass is smaller than this, then to leading order we need to solve this nonlinear oscillator. But once we do it, we get everything under systematic control. So let me just. No. Sorry, there is some number 1, 1, 3. Okay, what's an eigenvalue of Schrodinger equation with this potential? It's some order 1 number, right? It's phi to the 6 plus phi squared.
Oh, but there's no higher order term in lambda.
Not from this. Good. Sorry, what's happened? So you see this operator gamma that I used, it has corrections that are subleading in lambda.
Oh, I see.
Okay, remember there was this term, there was like lambda squared phi to the 5 term, etc., etc. So maybe let me write it here. So there is another term which is something like square root of lambda phi tilde to the 8. This phi tilde is already order 1 variable. Okay, and these are some things that we have computed that came from this from terms like this in pi. Okay, And from terms like this, there are now subleading corrections in this potential that in turn give subleading corrections to the eigenvalue. So it's plus lambda to the 3/4. And like we computed this piece, for example, explicitly. It's a mess of a calculation, but you can actually compute it. Okay? So this is the structure. Let me just sort of summarize with the intuitive picture that is behind this messy equations that I just claim. Okay, if you don't have any intuition, just sit down, take path integral in this order that I told you, and you derive these equations to any order you like in the coupling constant lambda. Okay, I just spelled out leading pieces, but subleading pieces they sort of mechanically you get them from just doing what I described. But the intuitive picture behind this is the following. So suppose we want to compute some 3-point functions, some points x1, x2, and x3. Okay. So it means that we need to compute this, say, P3 distribution. So first what we do, we keep coordinate distance fixed, but we go far in the past. Okay, and this is yeah, I'm basically done. And this is the physical. So physical distance goes to 0. So all those points evolve as 1. Then what happens when, say, one of those points x3 separates? Then there is some interaction over here that is given by this d term and by this gamma ij term that we can take into account perturbative. And then they again evolve independently. This independent one particle evolution, this is a strongly coupled evolution with the single particle operator. So this is the piece that needs to be done non-perturbative, but this is just one quantum mechanical problem that we can do. And then the same happens repeatedly with 2 other points, and then again they evolve independently. So the trick is the following, just to conclude, that we decided to take path integral in this order that we go to position space for long fields. And every time we need another long field, we just increase n, we insert another delta function. We'll take a path integral of that field at the last order. Okay, at this point we never need to take path integrals over long modes. We just solve this evolution equation and then take regular integrals over long modes that all turn out to be convergent as well behaved. But we need to solve like this single particle evolution in a strongly coupled way. Okay, yeah, and then I guess this this more or less concludes my talk. Is there something else important? Yeah, and as I said, then the short modes, we just treat them in perturbation theory with explicit IR cutoff, and then we add short and long contributions, and the cutoff cancels out between the two, which we just checked in a few examples. Okay, let me finish it. Don't hold you too long.